In this video, we'll discuss the applications of exponential and logarithmic functions. Now, when we solve any equations with exponential or logarithmic functions, the first thing we want to remember is that we're still following all of our rules of equation. So however you would solve a standard equation, make sure you still follow those rules. They are necessary. The distinction is that we now have logarithmic and exponential rules that can help us revise our equation to help us solve for the given unknown. For example, we can change an exponential function back to a logarithm or a logarithm back to an exponential function if that helps us, as well as remembering that we can separate logarithms and combine them back following the rules of multiplication of what's inside as well as division. So let's look at some examples to help us out. Here we have the log base 2 of the quantity x minus 5 plus 1/2 the log base 2 of 16 equals 6. Now, when we look at this, there's a lot going on, so we take it a bit at a time. So first thing, let's simplify having this coefficient out front by moving it back into the logarithm. So if I do that, that becomes log base 2 of 16 raised to the 1/2. And if we remember, 1/2 means square root. So we're really looking at the square root of 16, which is 4. Now we have the log base 2 of the quantity x minus 5 plus the log base 2 of 4 on this left side. If we remember our logarithm rules, when we have two logarithms with the same base being added, that is like taking their inside components and multiplying them together. So let's combine them back to one logarithm. And we're going to multiply our two interior components. So that's the quantity x minus 5 times 4. So I can distribute that 4 to both terms. So this is log base 2 of 4x minus 20 equals 6. So all I've done is take that left-hand expression and simplified it using my logarithmic rules. Now, when I look at this logarithm, I see that the unknown is inside the logarithm. So I need to convert this, instead of a logarithm, back to its exponential form. So our exponential form, remember, is the base raised to the y equals our x, or our inside. So this becomes 2 to the 6 equals 4x minus 20. Now 2 to the 6 is a number. It's 64. So now I add 20 to both sides and then divide by 4 and determine that my unknown is 21. Now let's say we have this equation here where we have 6e raised to the quantity x plus 8 equals 66. Let's follow our order of equations. So the first thing I'm going to do is divide both sides by 6 so that I can get this exponential function by itself. So now I have e raised to the x plus 8 equals 11. Now when I look at that, I have to remember that my variable or my unknown is in the exponent, so I need to convert this into its logarithmic state to get that unknown by itself. And what we remember is that when it is a base of e, that converts to the natural log. So we're going to do the natural log of the right-hand side will equal our exponent. So x plus 8 equals the natural log of 11. Those are equivalent statements, but now I can solve for my unknown. I'm going to subtract 8 from both sides, and then my exact answer is natural log of 11 minus 8. But if I need to then convert that into an approximate answer, I would get that that's approximately 2 and 3,979 10,000ths minus 8, which would be negative 5 and 6,021 10,000ths. Now, as we do application problems, we first want to look at them and determine what is it we're exactly trying to solve. Do we have an equation that can help us, and where does that unknown go into the equation? We also want to find and make sure we have all of our values that are going to help us solve that. So we substitute them in and then follow all of those same rules like we were doing on those problems before. So say we're looking at iodine 131 decay. It's a radioisotope that is used in medical diagnostics, such as testing how well a thyroid gland is working. It follows a decay model of A of t equals A sub 0 e raised to the negative 87 thousandths times t, where A sub 0 is the initial amount used in grams and A of t is the amount still in the body after t days. So say that if 151 grams of iodine 131 are used for a procedure, how much will still be in the body after 10 days. And we're going to round to the nearest hundredth of a gram. So there's a lot of information there. Let's take it one piece at a time and collect all our information. First, we know the equation that we're using for our decay model. We then are going to start looking for information to help us. Here, we're starting with 150 grams. We know that we're going for 10 days. And we want to know what's left in the body. So we can then substitute in for our original amount and the time. And as we do that, we just simplify one step at a time. And Desmos can help us with that simplification, or another calculator, so that we're looking at approximately being 62 and 8,427 10,000ths grams. Or since we're rounding to the hundredth, we look at our hundredth place, look to the right, and that's telling us we're going to keep that as 84 hundredths. So there are 62 and 84 hundredths grams of iodine 131 still in after 10 days. And again, pull as many decimals with you as possible. Use the answer button on your calculator to help you maintain decimals. Don't round too soon or your answer will be inaccurate. Now say that we have the procedure uses 150 grams of iodine 131. The doctor checks the patient's blood and sees there's still 30 grams of iodine 131 left in their system. How many days should have passed since the procedure? And we're going to round to the nearest tenth of a day. So again, we have our equation. We know the amount that we started with. And we know how much is left this time, which is the 30 grams. What we're solving for is time. So we think about, well, how can we go about solving for time? We're going to start with just following our order of equations. So we're going to divide both sides by the 150. That leaves us with 2/10. Now we look at that equation and say, well, this is an exponential with the unknown in my exponent. I need to convert this over to its logarithmic equation. So that's going to be the natural log of 2/10 equals 87 thousandths t. So now we can divide both sides by that negative 87 thousandths, and we can use our approximation for the natural log of 2/10 to get that that's approximately 18 and 4,993 10,000ths, or 18 and a half days have passed. Now let's look at one last problem. Say, again, the procedure uses iodine 131. The doctor checks the patient's blood and sees that there's 60 grams of iodine 131 left in the system after 13 days. And they want to know how much was originally used. So here, again, we're going to use that same equation. This time, we know what's left in the body, which is 60 grams. We know how long it's gone, which is 13 days. And we're trying to solve for that original amount. So as you've seen, we can solve for any of those components. So now here, e raised to the negative 87 thousandths times 13 is a number. I can then do e raised to that negative number. So I have some number times my unknown. I divide both sides by that value, and that will give me an approximation. And I want to round it to the hundredth of a gram. So if I look at the hundredths, that's 2, and to the right is a 5. So I'm going to round that up to 185 and 93 hundredths grams of iodine 131 were initially used for the procedure. And again, always make sure to pull as many of your decimal places from one line to the next to help confirm that your answer is as accurate as possible when you get to your final estimation.